Hey guys, it's Alex. In this video, I am going to walk you through an AP Physics 1 practice problem about uniform circular motion. Hope you enjoy. So in this particular uniform circular motion problem, we have a spacecraft right here with a mass of m that's in a clockwise circular orbit with a radius here around the Earth, which has a mass of me. And so for the first part, we are tasked with labeling the forces that are acting on the spacecraft. After switching to my drawing board, I will start by recreating the diagram by drawing the Earth, the orbiting spacecraft, the orbit that the spacecraft is in, and a line connecting the spacecraft to the Earth. This question is actually pretty easy because the only force that is acting on the spacecraft is the force of gravity that is exerted by the Earth. So I've gone ahead and drawn a green arrow pointing from the spacecraft to the Earth and labeled it F sub g, which means force of gravity. At this point, you may be wondering why the spacecraft can experience one unbalanced force, in this case the force of gravity, and not fall all the way back down to Earth. Well, the reason that it doesn't is because the spacecraft has a velocity that was derived from burning fuel in its engines, and so if no other force was applied, it would keep moving in the same direction as the orange vector. However, while in orbit, the spacecraft experiences an acceleration due to gravity, which pulls the spacecraft back towards Earth. This is what causes the circular motion of an orbit. It's the simultaneous movement of the spacecraft away from the planet and the acceleration back towards the planet because of gravity. The next question asks us to derive an equation for the orbital period t of the spacecraft in terms of mass of the spacecraft, mass of Earth, radius of the orbit, and other physical constants. To derive this equation, we'll start with the universal gravity equation and Newton's second law, both of which are provided on the AP equation sheet. So the universal gravity equation states that the force of gravity equals the gravity constant multiplied by m1, or the mass of the larger object, multiplied by m2, which is the mass of the satellite, all over the radius of the orbit squared. On the other hand, Newton's second law states that force net equals mass times acceleration. Since both of these equations have force in them, we can set them equal to each other. And in doing so, we can divide out the mass of the second object. So now we are left with the gravity constant times the mass of Earth over the radius squared equals acceleration. Using the formula for center-seeking acceleration, we can now substitute a for v squared over r. At this point, we can divide out one of the r's from each denominator and substitute for velocity. Velocity in this case equals circumference divided by time, or 2 pi r over t. Since we are solving for time and we have time squared in the denominator, we'll multiply both sides by t squared. Now in order to get t by itself, we'll use a little bit of algebraic magic and multiply both sides by the radius over the gravity constant times the mass of Earth. Finally, we'll take the square root of both sides, so we're left with period of orbit t equals the square root of 4 pi squared r cubed over the gravity constant times the mass of Earth. Something that should be noted here is that 4 pi squared, the gravity constant, and the mass of Earth are all constant numbers in this equation. So t, or the period of orbit, is directly proportional to the radius to the 3/2 power. Moving on to the next question, we have a second spacecraft with a mass of 2m that is placed in a new orbit, and we're asked if that orbit will be greater than, less than, or equal to the orbit of the previous spacecraft. By referring back to our previous equation that we just derived, we can see that the mass of the spacecraft is not there, and so adding or subtracting any weight from the mass of the spacecraft will not affect the period of orbit. With that being said, we can now safely answer the question as equal to. Finally, in part C, we are asked if the velocity of the first spacecraft will be greater than, less than, or equal to its original velocity once it has been moved to a new circular orbit with a radius greater than r. Since we know that center-seeking acceleration is equal to the square of velocity over the radius of the orbit, we can use that equation to solve this problem. As the spacecraft is moved into an orbit with a higher radius, the r value in our equation will increase. In addition, the spacecraft will experience a smaller gravitational force and will therefore have a lower acceleration. We now see that because the square of the velocity is being divided by a larger number and is set equal to a smaller number, it will decrease as the radius increases. We can now safely say that the velocity, when raised to a higher orbit, will be less than it was previously. To demonstrate question B, I loaded up my super high-tech modeling software and got to work. While I'm getting this rocket into orbit, I'll explain why being able to solve question B is so important. By deriving the equation for orbital period, we now know all of the variables that can manipulate it, including the mass of the body that the spacecraft is orbiting and the radius of the orbit. Using this new understanding of the equation, we now know which variables will change the outcome and which will not. So to prove to you that I'm not making all of this up, I have a lunar lander on the right and a command module that is connected to a service module on the left. That service module is full of a bunch of liquid oxidizer and fuel, and so it's a lot heavier than that lunar lander. I've rendezvoused both with each other and zeroed out their relative velocities so they're not moving farther away from each other or closer together. When I switch to the map screen, you can see that the trajectory of the lunar lander in green and the trajectory of the service module in blue are the same despite having very different masses. So this just goes to show that mass does not affect orbital period. What's up, guys? It's post-production Alex here. I hope you enjoyed that video. Hopefully you weren't too bored. I know if you were, I was too, so you're in good company. If you liked it, you know what to do. And until next time, I will see you later.